Okay. In the previous lecture, we considered the notion of spanning sets. And what we achieve is that using, let's say we have a subspace a collection of vectors W1 through WR is called a spanning set if the span of these vectors is W. Right, so W is the span of W1 through WR. So what this does for us is that we can describe vectors in W as linear combinations of W1 through WR. Okay. Now the question is, are we doing this efficiently? Okay. Or put it differently, are there any redundancy in writing a given vector in W as a linear combination of W1 through WR? And one observation we can make is the following. If W1 through WR are linearly dependent, which by definition means that there exists, let's say A1 through AR, real numbers, not O0, such that the linear combination of the W's with these A's as coefficients, A1 W1 plus A2 W2 plus plus AR WR is 0. Okay, that's being linear dependent tells us. And a key requirement is that these numbers A1 through AR, they are not all 0. So we may assume, not being all 0 means that at least one of them is not 0. Then we may just assume that, for example, AR is not 0, right? Then we can solve for WR from above, right? We have this relation among the W's, and AR is not 0, so I can therefore divide by AR, and I can move WR to the other side. That will give me WR to equal to A1 on minus AR, W1, plus A2 on minus AR, W2, plus AR minus 1 on minus AR, WR minus 1. Okay. Now, so this is saying that WR is a linear combination of the W1 through WR minus 1. So if we have a linear combination say B1 W1 plus B2 W2 plus BR WR. As we've said, we can describe vectors in W as linear combinations. So if we have such a linear combination, we can process it as follows. The vector to begin with, is B1 and W1 plus to BR WR. But I know that WR is written as the linear combination of WR1 through WR minus 1. Okay, so I can replace this WR here by the linear combination above. BR over here, WR gets replaced by this expression. Okay, and now what I can do is rewrite this by collecting terms proportional to the same vectors. So I have W1s here, I have W2s here, and I have WR minus 1 there. In doing that, I'm going to rewrite this as a linear combination of W1 through WR minus 1. Okay, so the answer is B1 minus BRA1 on AR W1 plus B2 minus BRA2 on AR W2. Finally, BR minus 1 minus BR AR minus 1 on AR WR minus 1. Now the point is that this is a linear combination of W1 through WR minus 1. Right? So we manage to use only W1 through WR minus 1 to express this vector in W. Okay, so what this means is that WR is redundant. If the purpose is to write vectors in W as linear combinations, you don't need WR. You just need W1 through WR minus 1. So, and this all happens because the vector here, W1 to WR, are linearly dependent. So if we are to express vectors in W efficiently as linear combinations, we should probably require that these W's or these vectors in our spanning set are not linearly dependent. So to be efficient, we should at least require that W1 through WR be linearly independent That would certainly avoid this redundant use. That requirement will certainly avoid this redundancy. And that leads to the following definition. Okay, so the setup is, again, you have a subspace W in Rn. The basis of W is a spanning set say W1 through WR, which is linearly independent. Okay, so the object we're defining here is what we call a basis. And as you can see in the definition, it's basically a basis is basically a spanning set that is also linearly independent. Okay. All right. Now, before we go on to consider some examples, let's put it as I don't know, a theorem. Okay, so suppose you have a basis that is, it's a spanning set and also linearly independent. And let's say, let's call it V, say let V be a vector in W. Then the statement of the theorem says that there is a unique way to write V as a linear combination of the W's. Okay, and the key point in the theorem is the word unique here. Being a basis, we know that V can be written as a linear combination of the W's because a basis must be a spanning set. But the requirement here, the statement here is that there's only one way. There's exactly one way of writing V as a linear combination of the W's. Okay, now proof. Proof is fairly straightforward. You want to prove that there's only one way to do it. So you assume that there are two ways, and that you conclude somehow that the two different ways, seemingly different ways, are actually the same way. Suppose V can be written in as linear combination of the W's in the following manner. That's V equal to A1 W1 plus A2 W2 plus blah, blah, blah. And also V equal to B1 W1 plus B2 W2 plus blah, blah, blah. PR WR. Okay. Then we know that if we take V and subtract V, we get a zero vector. That's natural. What we're going to do is, in fact, subtracting one linear combination from the other, like these. and then do what we all usually do, that is collect terms proportional to the same vector, W1 and W2, and likewise WR. If we do that, we will be looking at A1W1 minus B1W1 plus A2W2 minus B2W2 plus ARWR minus BRWR. And we again use one of the properties of scalar multiplication to write each of these terms as the difference between the two numbers times the vector. So A1 minus B1 times W1, A2 minus B2 times W2, plus AR minus BR times WR. Okay, so now what are we looking at? Over here, we have a linear combination of the W's, and this sequence of equality is telling us that this linear combination is equal to the zero vector. Now, because W1 through WR are linearly independent, right? Because being a basis, that's what's required. Because these guys are linear independent, the only way for their linear combination to equal to zero is for the coefficients to all equal to zero. We have A1 minus B1 equal to zero, A2 minus B2 equal to zero, and so on. AR minus BR equal to zero. Okay, so what does this mean? This means that the A's are equal to the B's. So in fact, these two linear combinations, these two linear combinations are identical linear combinations. Hence, you only have one way, exactly one way of writing V as a linear combination. Okay. Now, let's consider. So, I mean, this theorem tells us something very nice about basis for the purpose of describing vector space, right? Because with a basis, now we can write vector space. Sorry, we can write a subspace, elements of a subspace as linear combinations in a unique manner. And uniqueness is nice. So that means we don't have to make any additional choices when we do that. Okay, so example. Let's consider the following vectors. It's going to take some time because I want to write 5 vectors. 1, 2, 1, 1, 3, 1, 4, minus 1, 5, V4, 1, 0, 4, minus 1, and V5. Okay. 2, 5, 0, 2. Okay, these are all vectors in R4. And let W be their span. Now we can ask the following question. I mean, we certainly have V1 through V5 being a spanning set of W, right, by definition, by the construction of W. So we just have to worry about whether these 5 vectors are linearly independent or not. If they are not linearly independent, maybe we can throw out some vectors to get linear independent subset. Okay, so the question now is to find a subset of V1, V2, V3, V4, V5. That's the basis of W. Okay, we can try that. So to do this, what do we do? So we go back a little bit. In the discussion here, we've seen that if a spanning set is linearly dependent, then we have a non-trivial linear combination of the vectors equaling to 0 that we can use to get rid of one vector from the list, because one of them will be a linear combination of the rest. So we only need the rest to span the vector space in question. So that's what we're going to do. In this example, we will study the equation. We're trying to find out, first of all, whether these 5 vectors are linearly independent or not. And if they are not, find the explicit linear combination of them equaling the 0 vector and use it to get rid of one vector from the list. Okay, so we need to study this equation. Okay, how do we do this? I mean, we've seen by now a lot of equations like these. This is a way of writing a system of linear equations, right? So that is, so if I put, how do I want this? Okay, 1, 1, 2, minus 1, 1, 2, 1, 1, 1, 4, minus 1, 5, 1, 0, 4, minus 1, 2, 5, 0, 2, x1, x2, x3, x4, x5, equaling 0, 0, 0, 0. Okay, so this is a system, homogeneous system of linear equations. And of course, we've seen how to solve this system. And let me skip the details, but as you remember, what you're going to need to do is to write down the augmented matrix and turn it into reduced row echelon form. Solving the system will give us the following description of solutions. x1 equals to 2x3 minus x5. x2 to equal to minus 3x3 minus 2x5. x4 is x5. x3 and x5 are free. x3 is equal to x3. x5 is equal to x5. Okay, so apparently this system has infinitely many solutions, but what I just need one solution, one specific solution, one specific non-trivial solution, because all I want for our purpose is to find a non-trivial linear combination of the vectors v's equaling the zero vector. So for example, we can take x3 to equal to say 1, x5 equal to 0, and that will make x1 equal to 2, x2 equal to minus 3, and x4 equal to 0. Okay. Now with this solution chosen, we can plug it back into this linear equation. That gives us the following linear combination: 2v1 minus 3v2 plus v3 equal to 0. Oops. Right, we now have this one. Okay. I mean, this is a linear This is a linear combination of the v's obtained by a particular solution. Because we've chosen a particular solution, we're definitely losing information. We should therefore try to pick another solution and see what happens. This time, let's set x3 equal to 0 and x5 equals to 1. Then x1 becomes minus 1. x2 becomes minus 2. x4 becomes 1. So that will give us minus v1 minus 2v2, v3 is absent, plus v4 plus v5 equal to 0. Okay. Very good. So what are we going to do with this? Just like in the previous discussion, we're going to try to use each of these linear equations to get rid of one vector. So for example, in the first equation, I can get v3 to equal to minus 2v1 plus 3v2. Let's see, what do I want? In the second equation, I can get, say, v5 equal to v1 plus 2v2 minus v4. Okay. So what this is saying is that if we are looking at the span of v1 through v5, we don't need v3 and v5. So v3, v5 are redundant. Right, because they are expressed in terms of the others. Now, so we're left with v1, v2, and v4. And now my claim is that this set is linearly independent because, well, I mean, it's not meant to be immediately obvious, but you can check this. This can be checked by following the definition. Right, the definition of being linearly independent just leads you to consider a homogeneous system, which you'll solve and find that there's only one solution, the trivial one. Okay, so we therefore have a basis like these. Well, okay. So the process can actually be done fairly generally. So there is a more there's an algorithm for the more general situation. For the general situation, that is, if you have W being a span of the vectors W1 through WR, then to find a subset of W1 through WR, that is a basis of W, we proceed as follows. Step 1, solve the system. Oops. Again, the main idea is you're going to have to consider linear combinations of the W's equaling 0. Okay, you're going to solve the system using the method that we've described. And then you run into two possibilities. If the system has only the trivial solution, then W1 through WR are linearly independent. Hence a basis. Hence form a basis. Okay. Now otherwise, the system has infinitely many solutions. System has infinitely many solutions. Then it has free variables, right? As we've seen before. There are free variables and there are dependent variables. Okay. Now the process is fairly straightforward if you think about it. For each free variable xi, drop vi from the list, not vi, wi from the list. right? Each, just as you can see in the equation, each variable is attached with a vector, x1 with w1, x2 with w2, and so on. So if a variable xi is free, its associated wi should be removed from the list of w's, and the remaining collection will then form a basis. Is a basis of W, right? So now this is an algorithm for the more general situation. This algorithm produces for you, on a given spanning set, a subset that is a basis. Okay. Now, as you remember, one particular example of subspaces is the row space. Case of row space. Okay. Now we know the following. Say A is some doesn't really matter about the size, but let's say m times n matrix. And one thing that we've been doing over and over is to use row operations to turn it into reduced echelon form. So suppose B is row equivalent to A. That is, it's obtained from A by row operations. Then the theorem that we discussed before says that the row space, A and B have the same row space. Right, so for the purpose of finding a basis for the row space of A, we can also work with B, right? Because they give us the same row space. Now here's the observation. If B is in reduced row echelon form, then B looks like the following shape. I don't know. Let's see, 1 something 0 down here, and maybe there's 0 here and 1 something. Maybe there's a 1 down here, but 0 down below, and sorry, being reduced must mean that above this leading one should also be 0. Okay, so now there's an easy observation. There are two easy things to make at this point. The first thing is that by definition, row space, rows of B span the row space of A and B because they are the same row space. They have the same row space. Okay, that's just the definition of row space. Now the second observation is useful because it goes like this. The rows of B are in fact automatically linearly independent. Okay, and for that you can just look at the expression. Right, you're trying to form a linear combination of the rows, and you see that this must be 0 here too. You see that when you take the coefficients and multiply the coefficients to these rows respectively, you're gonna get the coefficient appearing in the place of the leading ones. If you add them together, you're just gonna get the leading ones up here. You get an entry. Maybe we should. Yeah. You're gonna get. You're gonna have entries that are equal to the coefficients. And this resulting linear combination is supposed to equal to the 0 vector. So all these entries are supposed to be 0. Therefore, the coefficients are 0, all of them. You get that the rows are linearly independent. So that tells us that rows of B form a basis of the row space of A. Okay, this is the consequence of this observation. Keep in mind that we are assuming that B is in reduced row echelon form. Okay, very good. So we can try to use this, right? I mean, this is convenient because every time we have, every time we have a bunch of vectors, if we put them into rows of a matrix, then I can use row operations to get to reduce echelon form. Then I can read off a basis. So the example above revisited. Example again. Let's take these vectors. V1, 1, 1, 2, minus 1. V2, 1, 2, 1, 1. V3, 1, 4, minus 1, 5. V4, 1, 0, 4, minus 1. V5, 2, 5, 0, 2. Okay. And we have, just like before, the span. The span of these 5 vectors being our vector space W or subspace W. What we're going to do in this example again is we'll find a basis of W that is not a subset of the V's, but using the above method. That's called a row space approach for simplicity. All right, so what does this mean? As you can see here, the row space approach works for row spaces. So we must turn the space that we have in question, that is W, into a row space. That's easy. All you have to do is put these vectors v1 through v5 into rows of a matrix. Well, you may say they are column vectors as written, but you can just flip them or transpose them, whichever you like to call it. Then, flip them, they'll become rows. So note that W is the row space of the following matrix. I'll just put these vectors into rows. 1, 2, 1, 1, 1, 4, minus 1, 5, 1, 0, 4, minus 1, 2, 5, 0, 2. Okay. Now, as we've explained in the method above, what we need to do now is to use row operations to get to reduced row echelon form. And I'll spare you the detailed calculation because that will take a while. The final answer will be like that. Okay. So now you immediately see that I should revisit the conclusion that we had. That is, over here, I shouldn't consider all the rows. In fact, it is possible, as you can see in this example, that some of the rows in B are 0 rows. But if we restrict our attention to non-zero rows, then everything I said is true. So here's what we're gonna need to do. We have now the matrix in reduced echelon form. They have 5 rows. The 3 of them are non-zero. 2 of them are 0 and they don't play a role. Therefore, these 3 non-zero rows will give us a basis for W. We get the following basis for W. That is, well, one last thing to do before you proceed is that, these are row vectors as you see. But when you write your final answer, remember to flip them back to column vectors. Okay. Okay, so that's the end of this lecture.